la pantalla.
Estamos en directo.
¿Se ve bien? ¿O le damos un
Un poquito a la izquierda.
Sí. Aquí está la pantalla.
Lo que pasa es que no quiero abrirlo.
Vale, entonces.
Yo lo veo bien, ¿no? Yo lo veo bien.
Sí, del fondo. Bien.
Sí,
Sí, sí, que se puede apagar el canal.
sí, que ayer se veía muy bien.
¿O se ve mejor en directo?
Sí.
¿O así?
No, yo de la otra manera.
¿Así?
Sí.
Ah, entonces bien.
¿Está lo que está?
Other slides in the platform of the
Okay, let's start. Remember what we have done so far. We are very happy because we managed to derive three very important quantum field theories, that means quantum electrodynamics, quantum chromodynamics, and the complete electroweak theory, just from a very generic symmetries. We have been using the Gates principle. If you find a symmetry which is global and is a symmetry of your free Lagrangian, you impose that this symmetry should be local, valid at any space-time point in the universe, and then you get the interaction of free. And we have got something which is very elegant, is simple, in 1-2 hours, depending on how fast you do the algebra, you can derive everything. And what is more important is fully correct. Every single measurement that we have done in the last 50 years trying to check these theories agrees with experiments. And it agrees with experiments with a quite high precision. In the case of quantum electrodynamics, we saw the anomalous magnetic moment of the electron, where we predict 15 significant digits, and they agree with experiment. In the case of QCD, since the coupling is stronger, precision is not so good, but we are computing observables with precisions of the order of period, which is quite amazing for the nuclear force. And in the electroweak theory, I told you that if you don't pretend to be too precise, you just use it as a classical field theory, that means compute things at lowest order in perturbation theory, then everything is correct, so we know that the Lagrangian is correct, and you can even reach precision of the order of the 1%. But if you want to be more precise than that, you need to implement quantum corrections, and there you find a problem. Okay? At this level, everything is very elegant because you only have three inputs: the value of the strong coupling, the value of the electromagnetic coupling, and then the Weinberg mixing angle that we introduced yesterday. Okay? If you want, this is equivalent to the coupling of the SL3 theory, the coupling of the SL2 theory, and the coupling of the U1 hypercharge. But the same gate symmetry that predicts all the interactions also forces all particles in the universe to be massless. And this, of course, is not correct. If you try to introduce the masses by hand, because we know that the Lagrangian is that heavy, we know that the clock is heavy, we know that even the electron has a mass. It's tiny, but it has a mass. If you introduce those masses by hand, your theory does not have any. I don't know about electroweak theory. This is not a problem for electrodynamics, it's not a problem for chromodynamics, but it is a problem for the electroweak theory because you differentiate between left and right. And a mass telling the Lagrangians mixes the left and right polarizations. You cannot put the masses by hand because this destroys something called renormalizability. If you want, it destroys the mathematical consistency of your theory. So that you compute logos ordering perturbation theory, everything is fine, but in the moment you compute the first quantum correction, you get infinity. Doesn't matter what you compute, you always get it. So you need the symmetry because it's the symmetry the thing that gives consistency to your theory, but at the same time, you need the symmetry to be broken in some way because otherwise you cannot get masses. And the way to do that is using the phenomenon of spontaneous symmetry breaking. That means your Lagrangian is always symmetric, so symmetry is perfect, but your vacuum is not symmetric. If you want the spectrum associated to your Hamiltonian is not symmetric. And before I go into details, remember that where the problem comes from, a spin one particle without mass, I'm thinking about the photon. You know from classical electrodynamics, a photon only has two polarizations. This is true for the photon, it's true for the W, and it's true for the Z. If they don't have mass, they only have transverse polarizations. However, you also know from quantum mechanics that a massive spin one particle has three polarizations. +1, -1, and 0. So one of the polarizations is polarization 0, it's called also longitudinal polarization, is missing. So if you really want to give masses to your gauge bosons, you need to add 1 degree of freedom for each gauge boson that you want to get a mass. So you have the W plus, the W minus, and the Z. Therefore, you need to add to your Lagrangian 3 degrees of freedom in some way. Otherwise, it's impossible. Okay, let's remember what the spontaneous symmetry breaking is. So you have this nice potential with a donkey. The potential has a perfect left-right symmetry. And that means that instead of having 1 minimum, it has 2 minimum. They are identical because the potential is symmetric. But in order to do quantum physics, you need to choose a vacuum. You need to choose what is your fundamental state. So what you do is you choose your fundamental state. In quantum field theory, we call that the vacuum of the system. And now you start doing the small perturbations around this fundamental state. And these perturbations, if are in the direction of going up the hill, they cost energy. So perturbations along this direction correspond to particles that have a mass. So the quantum associated with these perturbations has a mass because in order to move, you need energy. There is a difference between this flat screen and the real world. And the difference is that in this flat screen, the symmetry is a discrete symmetry, left, right. However, if I add the third dimension, the discrete symmetry transforms into a continuous symmetry. And the physics of a continuous symmetry is totally different from the symmetry of the discrete left-right symmetry. Now, instead of two minima, you have an infinite number of states of minimum energy, all of them with exactly the same energy. So you have a symmetry around this bubble. And now you can choose any point along this dashed line as your reference. It doesn't matter which point you choose, because all of them are identical for the physics point of view. But you choose one. And in the moment you choose one, you will have perturbations going up the hill, a massive particle, and perturbations along the valley. And a perturbation in this direction corresponds just to moving from one minimum to another minimum, but they have exactly the same energy. Therefore, these perturbations don't cost any energy. They correspond to massless particles. So this is a Holston boson, and this kind of Holston bosons appear in many physical systems. So what this has to do with electroweak theory, a priori, it doesn't look like it has anything to do. It makes the problem worse because you are just adding more states without mass. Your problem is to find out mass. The big discovery of Higgs and the other people that worked at the Higgs mechanism was that they found a mechanism based on the Holston theorem, which was able to give masses to the X particles. They didn't apply it to any system of physical relevance. It was just an academic exercise, and nobody took really attention to that. Okay, but the principle was there. So let me try to explain the principle very easily with this kind of equations. So let's take a complex scalar field that means 2 degrees of freedom is complex, and wave function in quantum mechanics. You have a kinetic term and you have a potential, and I take a potential which has a quadratic piece and a quartic piece. By construction, my potential only depends on the modulus of the field, because it only appears as phi r. That means that by construction, the potential has a phase here. And the phase is the particle. Now the potential has 2 parameters. Mu, that I have put mu squared, just that you remember that signs are important, and lambda. Lambda should be always positive, because otherwise the potential will not have any meaning. Okay? If you take a lambda negative, the potential falls down more and more and more, and therefore you can get up to minus infinite energies, which does not make any sense. So lambda should be positive. What about mu squared? The normal situation that you always find doing physics is that mu squared is positive. That's why I put the square. And then the potential looks like that. And there is a single minimum. And then this term just corresponds to the mass term of the scalar field. So this field is describing a spin 0 particle, and its antiparticle, it's a complex field, it has 2 degrees of freedom, and both the particle and the antiparticle have the same mass, and the mass is mu. Remember the plane Gordon Lagrangian that was derivative minus m squared. And so mu is the mass of the scalar. And the minima just correspond to the normal configurations where the field is 0. This is always your default choice. What happens if I allow mu squared to be negative? Then I get the wrong potential. Okay? Because then I get a potential that, of course, has this symmetry. That's the phase symmetry, which is always there. But now there are an infinite number of different minima, all of them along this valley. And all these minima, you just take the derivative of the potential and compute what is the value that minimizes the potential, corresponds to a value of the field which is not at zero, it's not here, it's here. And it's just the square root of minus mu squared divided by 2. And I will call that vacuum expectation value divided by the square root of 2. That's the convenient normalization that everybody uses. And of course, it's a positive number. Okay, so this is the distance between the origin and the circle that defines the vacuum. Yes? Well, if you get worried about that, instead of mu square, call it omega over there. Okay? I just put the square to remember, to make you aware that you are in some odd configuration, because naively you will expect this parameter to be positive, because you are used to this. Okay? Whether the mu defined in this way is real or imaginary, I don't know, because the only thing that is going to be relevant is mu square. Okay? See, minus mu square, this is positive. Okay, more questions? Yes?
Does it mean the mass of the square field?
No. Okay, here it was. Now the situation is different. Now you need to analyze that more carefully. So let me parameterize the field. Remember, it's a field and the complex conjugate of the field, so it has a real and imaginary component. But I can always parameterize that as the modulus and the phase. And now the modulus I define as V plus phi 1, where now phi 1 is a real field, divided by a square root of 2, so that the minima corresponds to field equal to 0. So I have just shifted the origin of my field times a phase that I put 2. And now, when I am doing that, and I say, okay, I use this to quantize my field. At this point, I have made a choice of vacuum, of what is the fundamental state of my system. I could take any of the points along the circle as a fundamental state, but I have taken the value phi 2 equal to 0 as my default fundamental state. So that I start from 0, making perturbations. Of course, I could start from any point, because the potential is symmetric, only depends on the points. So my Lagrangian is fully symmetric under the phase transformation. But once I say I start from this point and start building my quantum theory with the small perturbations around this particular point, I am breaking the symmetries from that. Which means I break the symmetry without breaking the symmetry. The symmetry is always there. It's just my mathematical formula looks like if I would have broken the symmetry, which is continuous. And now you can say, okay, let's parameterize the potential in terms of these two fields, which are real. And of course, the potential looks like that. There is no dependence on the second field, because there is no dependence on the phase. Which means that the second field does not have any mass. There is no mass term. In order to have a mass, I should see in the potential a quadratic term in phi 2. And it is not there. So, phi 2 that corresponds to excitations along the circle is a Boston motion, a massless particle. And now, phi 1 that corresponds to excitations along the hill has a mass which of course is positive, that is equal to minus twice mu squared. Remember, before there were two particles of mass, or a particle and an antiparticle of mass mu, 2 degrees of freedom. Okay? Now, the factor of 2 goes into the mass of the first component. So this is just the Boston mechanism. It's exactly the same as I have done with the bumpy, but now with equations. Okay. Now let's go to the standard model. The basic ingredients are Higgs and all the other groups that were working on that just stopped here. They did a few academic examples more, and they were just showing that there was a Boston theorem, and then they were using this Boston theorem, for instance, in a theory like electromagnetism, where there is an abelian symmetry, and showing that it was possible to generate a mass flow that you don't want. But what Weinberg and Salam did was to implement this idea into the standard model itself. They took the so-called electroweak model of Glashow that had the problem of the masses, and is something similar to what I have been explaining to you in the previous lectures, and they introduce this potential. It's the same potential. The only difference is that here I just take one complex scalar field. Since we want to implement that into the SE2 cross U1 gauge theory, we need to put a doublet of complex fields that transforms in the proper way under the SE2 symmetry. So Weinberg took a doublet, so you have one complex field and another complex field. You want this doublet to couple to the W, so the difference in electric charge between the two fields should be 1. You want this to couple consistently with the electroweak theory we derived yesterday. And remember, yesterday I proved that the hypercharge should be equal to the electric charge minus P3, the isospin, if we want to reproduce correctly electromagnetism. So this tells you that if you want a charge scalar and a neutral scalar, your hypercharge should be 1 over 2. So that 1 minus 1/2 is 1 over 2, 0 minus 1/2 is 1 over 2. Okay, so everything is fixed, which means that I can couple this doublet to the gauge bosons or the gauge theory that we have constructed with the gauge bosons. The only thing that you need to change is the normal derivative to a covariant derivative. And the covariant derivative, it has the normal structure coupling to W1, W2, and W3 with the SU2 coupling G. Okay. And the U1 piece, where you couple to the U1 gauge field mu with an hypercharge equal to 1 over 2. And coupling G prime is a coupling of the U1. So you just take this scalar Lagrangian and you add the scalar Lagrangian by hand to the electroweak model. Okay? And you don't bother asking what those fields are. You are just desperate, you want to introduce masses, so you know that you need to add additional degrees of freedom to explain the longitudinal polarizations of the gauge bosons. So that's the simplest thing that you can do. Okay. Let's see what happens. Now I parameterize in the same way, the phase and the model. Okay, because I have my potential. My potential looks like that. It's the same potential I have here, except for one thing. Here, I only have a phase symmetry. Okay, so everything is very simple. While here, I have a doublet. So I can write the doublet as the modulus times the phase, but the phase is not just a phase. It contains three phases because it's an SU2 rotation. You have four fields. So I have here three fields, and I have here another field. I have my 4 degrees of freedom, my 4 real fields. I know that there is a vacuum expectation value. It's the same I had before. It only depends on this piece. That's what minimizes the potential. And V squared is minus mu squared divided by lambda. It's the same relation I have here. So I have put the vacuum expectation value in the neutral field. Why I have done that? Because if I give a vacuum expectation value to some electrically charged field, then I will be putting an electric charge in the vacuum. And that means that the conservation of electric charge will be wrong. And we don't want to do that. We want to preserve electromagnetism as a true symmetry in the system. Therefore, charges should be conserved. So the only field that can acquire a vacuum expectation value is the neutron. So I am writing that as 0 the charge 1, some vacuum expectation value the neutral 1. I parameterize the excitations along the field with this real scalar field H. That is what you call usually the Higgs field. And then excitations along the valley. The valley now is a 3-dimensional valley because there are 3 degrees of freedom that correspond to the 3 parameters of the SUT rotation. Okay? And these parameters are not physical a priori because you have Higgs invariants. Okay? You can always rotate, but if you rotate your full level. So that means that since I have an SU2 left invariance in my full Lagrangian, I can eliminate these 3 degrees of freedom in some way. Because I can fix the gauge. That's when you work in electromagnetism, you say, A mu has 4 degrees of freedom. The scalar potential and the vector potential. So the electromagnetic field has 4 degrees of freedom. But the only thing that is physically relevant are the electric and magnetic fields. It's F, mu, mu. And you can always do gauge transformations. And you have 2 degrees of freedom that you can eliminate. You can impose, for instance, the Lorentz condition, divergence of the electromagnetic field equal to 0, and then sometimes you impose I0 equal to 0. Impose 2 conditions. Which conditions you impose is irrelevant. You do what is easier for the particular exercise that you are trying to solve. Because in any choice of gauge, the predictions of electromagnetism are the same. But you can fix the gauge if this makes your life easy. Well, here, I can fix the gauge, saying I do an SU2 rotation such that I eliminate these 3 degrees of freedom. And the only degree of freedom that remains is this H. Okay. What happens if I work in this particular gauge? Well, if I work in this particular gauge, that's called the unitary gauge. Then take the product of the 2 derivatives, this piece of the Lagrangian, because the potential only depends on H, in any gauge, because only depends on the module. Okay? The dependence with the other fields is here. So, in this particular choice of gauge, the derivatives, since this is eliminated, just give me a derivative term for the fixed field. A real spectrum. Now the rest, the cross terms with 1 derivative, they disappear. You can set that very easily. But now let's look to this. You have derivative times derivative, which means that you are going to generate a quadratic term in the W form. W. And this quadratic term will contain 2 factors of G and 2 factors of V plus H. So it will be G squared times V plus H squared times some factor, okay? So which turns out to be a factor of 1 over 2 squared. So what you get is a mass term for the W form. And this maps out. You get 1 plus H over V squared. I have just taken that out and have factor V in front, times a coefficient that is 1 over 2 G times vacuum expectation value squared. So the W has a quite mass in a magic way. Now you work out the rest, because now this is for the W plus and W minus, but then you have the W3 and the D. And remember the W3 and D, there is a mixture of them that is the photon, and there is a mixture of them that is the W, so you need to do a slight algebra. But what you find is that only the Z field gets a mass. And the mass that it gets is exactly the same as the W, except for a factor of sinus of theta. And the photon does not get any mass. Why the photon does not get any mass? Because I have broken spontaneously the symmetry in such a way that I preserve the electromagnetism exactly. The vacuum expectation value is in the network field, not in the charge. Otherwise, it would have been a disaster. We don't want much for the phone. So, in this particular gauge, and only in this particular gauge, the physics is now the physics of 3 massive states, which are the W plus, W minus, and Z, plus a Higgs boson, plus a, which is massless. If you go to any other gauge, things will appear to be more complicated, because then you will see the Goldstones, you will see massless Zs, massless Ws, okay? But the physical predictions that you will get for any observable will be the same, because of gauge invariance. Gauge invariance is there. So the predictions of your theory will correspond to the predictions of a theory with 3 massive components. Okay? Now you could think that, okay, there is something here that it looks as magic. Okay? But I recommend you just do the algebra, this trivial algebra, get convinced by yourself that that's the algebraic result. And now let's think what is going on. What do we have in our laboratory? We have the gauge theory, which is fully symmetric under gauge transformation, and therefore it contains gauge bosons which are exactly massless. So I forget about the photon, okay? I have 3 massless gauge bosons. Each of them has 2 polarizations, so I have 6 degrees of freedom. But I have added the downfield potential, which means that I have added 3 bosons, which are also massless. 6 plus 3 is 9. When I go to the unitary gauge, the Goldstones have disappeared, but in this unitary gauge, I see 3 massive gauge particles. Each of them has 3 polarizations, the same 9 degrees of freedom, the same physics. So the mathematics is the same. It's just the physical interpretation in the unitary gauge is easier for us. Because in the unitary gauge, you identify immediately you have a massive particle because I see that. But the gauge symmetry is exact guarantees that in any other gauge you will get the same predictions for your observations. Okay, is that clear? So we have found a way to get masses for the gauge bosons without breaking this. But of course, it was necessary to add these 3 degrees of freedom. Otherwise, it would have been impossible. The odd thing or the strange thing, if you want, about the standard model is that instead of adding 3, you add 4. And you add 4 because it's the simplest way to put up this mechanism. But it's perfectly possible to do it without the 4 degree of freedom, just you get a more complicated freedom with this number. Which means that everybody was very happy when Weinberg and Salam showed that. But that was just a mathematical argument. Nobody was convinced that really such an object would necessarily be there. Okay, maybe not. Well, it was clear that Albert was solving a problem of the model, and whether this object exists or not exists, that was delayed for the future. Maybe somebody will understand that better. Okay. So this degree of freedom too much is what finally has turned out to be the most important key of the standard model. It is the key we are studying nowadays. Tomorrow I will make a few comments about that. What about leptons? Oh, sorry, fermions. Well, fermions in the standard model also have the same problem. Since left and right chiralities transform in different ways under the gauge group, you cannot build a mass term for the fermions directly because left component times right component is not gauge invariant. But once you have introduced the scalar doublet, with the scalar doublet, I can build these structures which are perfectly invariant both as you left and you want hypercharge transformations. So here you have a doublet. The scalar is another doublet. So the doublet degrees of freedom, the SU2 degrees of freedom plus is an SU2 scalar. Another fermionic degrees of freedom plus with this right-handed quark. And now if you analyze the hypercharges, this also represents the hypercharge. And I can write these 2 different terms for the quarks, where this is the C conjugate, the charge conjugate of the scalar field. So this is field positive, field neutral, this field neutral complex conjugate, and this after a minus sign that comes from Whiplash speed is the negative one. So this is the conjugate field and the charge conjugation. Therefore, instead of having hypercharge equal 1 or 2, it will have the opposite of hypercharge. So this is also invariant. And for leptons, you can copy the 2 things. I just have copied the first one because I didn't put a right-handed thing. But if you want to put it, you just add an additional there. No problem. And now you do spontaneous symmetry breaking, which means you take this and in the vacuum is 0 the first component, vacuum expectation value over square root of the second component, of course, times 1 plus h over v, which is why I'm just taking this thing here and looking what is the particular value for field equal to 0. And then you see what happens. Look here. Is the lowest entry of the doublet, so it's going to couple the left with the right. That's a mass term for the lamp core. This is the vacuum expectation value is here in the upper component, so it's going to couple up bar left with up right. That's a mass term for the upper. So what you get is this Lagrangian in the unitary gauge. So you get mass term for all your fermions times 1 plus Higgs field divided by vacuum expectation value. So you get very happy. Now all your particles have mass, but you are unable to predict the masses, because the masses are just these couplings that you don't know where they come from, times the vacuum expectation value of the Higgs field divided by the square of it. So you lose predictivity, but you have masses. And of course, if you measure the masses, then you predict that the couplings of the Higgs to the fermions are proportional to mass divided by vacuum expectation value. While the couplings of the Higgs particle to the gauge field are proportional also to masses, but this time to mass squared. So the gauge bosons couple proportional to their mass squared, the fermions couple proportional to their mass to a single one. In the case of the gauge bosons, you predict the masses. It's vacuum expectation value times the absolute coupling. So if you know the vacuum expectation value and you know the coupling, you predict the mass of the W, you predict the mass of the Z. In the case of the fermions, you don't really have any prediction, because first you need to measure the coupling, and to measure the coupling, you need to measure the Higgs boson first. So you have measured the masses. So let me clarify that in a factorial. Everybody in this world, in the universe, gets the mass through its interaction with the Higgs field. So if you can visualize that in intuitive terms, think W boson is traveling through a space-time. The space-time is fitted up with the Higgs field. Remember, vacuum in the vacuum, it has a value. Okay? It's your vacuum expectation value. And then when the W is traveling through space-time, the W fills the Higgs field. And if you want the interaction of the Higgs field is freezing the W, is lowering its velocity. Okay? And therefore the W is acquiring mass. It's a dynamical effect. The same for the Z, the same for the top, while the photons don't get a mass, because they don't feel the Higgs field. They don't interact with this Higgs vacuum that is everywhere. Okay? So, if this mechanism is true, we have a new interaction. This new interaction is a field that is all over space-time. And every single particle, when it travels through space-time, interacts with this field and gets a mass from this interaction as a dynamical effect. Okay? Here you should be careful with one thing. Don't confuse the masses of the elementary particle with the macroscopic term mass. Okay. The masses we are using in the macroscopic world come from the masses of the atoms. And the masses of the atoms come basically from the proton and neutron mass. But the proton and neutron mass are not generated by the Higgs mechanism. The Higgs mechanism generates the mass of the up quark and the mass of the down quark. But those masses are completely negligible compared to the proton mass. Okay, the up and down masses are ordered 3, 4, 5 MeV. The proton mass is ordered 1 GeV. The proton mass is pure energy of its strong interaction. It's binding energy. The Higgs mechanism does not generate this bonding energy, therefore it does not generate the mass of the universe. What it generates is the mass of the elementary particles. Both the H bosons and the fermions. Is that clear? Okay. Does it work? It does. Remember, the Higgs mechanism was invented in 1964, 50 years ago. 50 is a very long time. And already in 79, Weinberg, Blashow, and Salah got the Nobel Prize. And everything they did was based on the Higgs mechanism. And nobody knew whether the Higgs mechanism was right or not. But the theory was right because it was successful. Already in 79, the experimental success of the theory was impressive. Impressive enough to get a Nobel Prize. And from 79 to the year of the Higgs discovery, which was 2012, there have been, I didn't count exactly, but at least 5, 6, or 7 Nobel Prizes, different Nobel Prizes, given to particular aspects of the standard model. And all of them need the Higgs mechanism to make sense. So it means that the theory is successful in a quite spectacular way, and nobody knew whether the Higgs was there or was just an implementation. So let's see some predictions. For instance, the first one, we got this nice relation from the Higgs mechanism, and this relation tells you that the W mass is lower than the Z mass, because cosine of theta should be smaller than 1. We have measured the Z, we have measured the W, and they, of course, satisfy this relation. Remember that in 1964, the W and the Z have not been discovered yet. But in 1964, we didn't know even whether the Z was a real particle. We had things about the W, but not about the Z. Okay, since sinus square of theta is equal to 1 minus cosinus square of theta, so if I take the measured values of the W and the Z, I learn that sinus square of theta W is 0.223. Okay, remember this now. Something around point. Good. There is another thing that we know since many, many years ago, and it's muon decay. In muon decay, a muon decays into an electron and 2 missing neutrinos. That's a beta decay. And the W was introduced to understand this type of beta decays. So we didn't know whether the W was a real particle or not, but it was what it was needed in order to understand that. The transition amplitude of this type of process will have 2 couplings to the W, so G squared, that's an SU2 coupling, and a W propagator, that is NW squared minus Q squared in the denominator. Since the W mass is very, very heavy compared with the muon, and the momentum transfer along this line is smaller than the muon mass, it cannot be larger than that. This Q squared is completely negligible with respect to the W mass squared, which means that experimentally you don't see the propagation of anything. What you see is a muon that decays in a single space-time point into 3 particles, with a coupling that was called the Fermi coupling constant, and with a normalization that was chosen a long time ago by Fermi. I can relate now this with G over NW squared, so those are the factors I need to relate both. Which means that just knowing the Fermi coupling constant, I know G divided by NW. And the Fermi coupling constant, you get immediately from the mean life. The decay amplitude is proportional to GF, probability is proportional to GF squared. GF has dimensions of energy to the -2. GF squared has dimensions of energy to the -4. In order to get a decay width, you need something with dimensions of energy to the 5th power. And the only thing with dimensions here is the mass. Everything else is irrelevant. And this factor 192 over pi to the cube, you can put it by hand, that's the space of 3 particles. Without doing any calculation, you will get the right result, maybe you can miss a factor of 2 over 3 or something like that, a factor of 2 over 1. And that's why, from the muon lifetime, we knew many, many years ago that this kind of bigger decays should correspond to some intermediate particle of over 100 GeV that people call that. Okay? Now we have a theory that contains that, so now we can be more precise. Okay. This is the calculation. You measure the muon lifetime. That means that you get a very precise number for the thermic coupling constant just from the muon lifetime. So now I can do things in a different way. Instead of using the Z mass, I use the thermic coupling, something that a priori is unrelated. I use the value of the W mass, and I remember that G is E divided by sinus of theta W. We got this relation yesterday, imposing that the standard model of electroweak interactions reproduces quantum electromechanics. And we got this relation. If you put these relations together, you can fix what is V, because vacuum expectation value is equal to W mass divided by G and to a factor of 2. So vacuum expectation value is equal to a square root of 2. The Fermi coupling constant is G divided by NW squared. So you take the square root of that and you get what you need here. So the Fermi coupling constant is telling you what is the value of the vacuum expectation value of the fixed. So from muon decay, we know that it's around 250 G at quite high mass scale compared to muon. And now, using the W mass and this relation, we can write sinus square of theta W as function of the finite structure constant, the Fermi coupling, and the W mass. No information whatsoever from the Z mass. And instead of 0.223, we get 0.215. The two numbers agree. The two of them tell you that the result is 0.22. And there is a difference in the third digit, which means that you have enough precision to look for quantum corrections. Because those are the predictions you get in a naive way from lower order interpretation. And quantum corrections, if the theory is correct, should describe the very tiny difference between this number and this number. Okay, let's count parameters. We have two parameters in the gauge theory. I forget now about UCD. So the SU2 times U1 gauge theory has the SU2 coupling and the U1 coupling. And we were very happy because we only had two parameters. Introducing the Higgs sector, we have doubled the number of parameters. But okay, 4 parameters is not so bad. And these 4 parameters I can trade by 4 different measurements. I can make many choices. So what you do is you look to the things that have been measured more precisely, and those are the finite structure constant, the Fermi coupling, and the Z mass. And the 4th parameter, this lambda, remember what it is? This lambda is the quartic term in the Higgs potential. There is no way you can access this parameter without discovering Higgs. This parameter is related to the Higgs mass itself. So nowadays, the choice of constant is for the fourth parameter, we choose the Higgs mass, which starts to be quite well determined nowadays. But in the next slide, I will forget about this fourth parameter. I will just show predictions with the first three, because those were the things we knew before the Higgs discovery. So let's do the same exercise I have done before with muon decay, but now I do it in a different way, because before I was using MW as the input. Now I am not using MW, I am using MZ, because MZ is better non-experimental. But I use the same relations. Sinus square of theta is 1 minus the ratio of variables of masses squared, and there is a relation between the W mass, theta W, alpha, and the Fermi coupling constant. Okay. So knowing these three numbers, I predict sinus square of theta W, and I predict the W mass. Now you see sinus square of theta W is slightly different from what I had before. 0.21 instead of 0.22. So changing inputs, higher order corrections are slightly different, so we are really sensitive. But that's interesting because we want to check the theory of the quantum level. And with the Higgs mechanism, the theory is perfectly defined mathematically to any level of perturbation. And what about the W mass? We predict it to be 80.94, which is slightly out of the experimental measurement, just slightly. But now, remember one important correction that I was talking yesterday, and is at the quantum level, the value of alpha is not the defined structure constant. Once you do quantum corrections, you get an effective value of alpha which depends on the energy that you are doing experiments. And this effective value of alpha includes higher order electromagnetic corrections. And if I am doing physics of the W and the Z, the correct scale is the Z mass, it's the electroweak scale. And at the electroweak scale, alpha minus 1 is not 137, it's around 129. This is it. Remember, the electromagnetic coupling grows with energy. So if I change this input by this one, and notice that I pay a very big price in precision. Here, the precision is impressive for the finest structure constant. Here, the precision is just at the limit, because usually it's important in order to get this number. You pay a price. But okay, I change this input by this input and see how things change. This 0.212 now is 0.231. So extremely sensitive to quantum corrections. And the W mass, now it has flipped and went to the other side of the experimental value. The experimental value is in the middle between the two predictions. So again, quantum corrections are important at the level of precision that we have. So that's what I already showed yesterday. That explains the change on the value of alpha. You are creating these dipoles at the quantum level. The photon field that propagates between one charge and the other charge is creating particle-antiparticle pairs all the time. So if you separate the charge that creates the field and the charge that is filling the field, you separate them, there are many dipoles in the middle, and the charge is still. So this particle is looking to the charge that generates the field of this particle, and see what it sees is a charge that is smaller than the real one. If you approach the two charges, there is less space in the middle, vacuum space if you want. There are less dipoles, there is less screening. So the charge grows, the density of the electromagnetic field grows. Yeah, the wall effect explaining this quantum correction. Okay, let's look to something more fancy. In the standard electronic theory, we have completely predicted the couplings of the Z in the different fermions. Of course, they contain G, and they contain some vector and some axial part, which depends on the electric charge of sinus square of theta W, so this vector and axial couplings. Okay. You can collect all that in this simple formula, where it appears a Fermi coupling. These couplings were given in one of the tables I showed yesterday. Okay, so they are numbers before the 1. Then you have here the number, the effective number of colors. So for leptons, this is 1. For quarks, it will be 3. But quarks interact strongly, the final quark and anti-quark, so there are implicitly corrections. So for quarks, this factor is about 3.12. We don't need to be more precise. We know this factor to order alpha s to the 4th order. So we know it very, very precise. So let me just compare the decays of the Z into nothing. This is called the invisible decay of the Z, with the decay of the Z into electrons, the electron positive. What means that you don't see anything? The Z has decayed into neutrinos. And since you have measured the total decay width of the Z, and you have measured the decay width of the Z, electrons, muons, taus, and quarks, you can experimentally determine what is the invisible part of the decay width that you don't see. And of course, this invisible part will be equal to the decay width into one family of neutrinos times the number of neutrino families that are in the Z. Have an open decay. So the only difference here is just these factors. So in the case of the neutrinos, it's 1 and 1. In the case of the electron, this is the vector coupling, this is the axial coupling. So you get this very, very simple relation. So in order to predict this ratio, you just need to tell what is the value of sinus squared of theta W. And with my 4 inputs, remember, I had 2 different values of sinus squared of theta W, depending whether I was using the final structure constant or the value of alpha and the Z mass. So there is a slight difference. The third digit, if you want. Okay? It's a tiny difference which corresponds to include or not to include the quantum correction corresponding to the vacuum polarization. Transforming this number, this is the experimental number. So depending on what you use, you get from experiment that the number of neutrino families is 3.04 or is 2.99. So it's if you include the full set of non-quantum corrections to this decay width, okay, so everything is known to one loop, basically the most important corrections to second order interpolation, third order interpolation, 32 loops, they are known already, that's the number you get. The number of neutrino families is 3.0026 plus minus 0.0061. So there are only 3 numbers. That was one of the most important achievements of lab. Of course, this does not prove that there are only 3 families. It only tells you that if a 4th family exists, it's a very exotic family, because the set should not be allowed to decay in this family, which means that the neutrinos of the 4th family should weigh more than 45 G. And you will not call that neutrino. Look a much more exotic object. Okay, in the same way, if you just compare Z going to quarks, general point, quadrants, you sum over all possible quarks, with Z going to electrons, that's the experimental number. Now you are looking into that, so you are testing QCD. Just from this measurement, you can fix the strong coupling constant with a precision which is at the millimeter. So strong interactions are very strong, but we have managed to get this type of precisions and variance. Okay, so far I have been only talking about one quantum correction. Here I have included everything. Okay? But I was showing you just the vacuum polarization of the photon. But in the electroweak theory, there are many more quantum corrections, which means interesting physics, because in the same way that the photon has a self-energy, the W and the Z also have self-energies. And these self-energies include the top. And the top is an extremely heavy object. And therefore, it generates corrections that grow as the square of the top mass, which is a very, very large one. Those corrections are important. But the Z and the W also couple to the Higgs. The Higgs couple to the W's. So, for instance, I can draw this diagram over there. The W self-energy can make a Higgs particle and a W, which also close, and finally you come back to the W. So the Higgs boson also contributes to this self-energy. This contribution is smaller, it gives correction which grow logarithmically with the Higgs mass. And then there are other processes where, for instance, the top appears. That's something I computed many years ago. The Z decays into a B and a B bar, bottom. But the bottom is a partner of the top. Therefore, they come together. A priori, the Z can decay into a top and an antitop. It cannot, because the top antitop is much heavier than the Z. But it can create a virtual top-antitop pair. And then at the loop level, there is an exchange of a W, and the top gets transformed into a bottom, the antitop gets transformed into an antibottom, which means that the top quark contributes to the decay width of the Z into the B bottom. And when this was computed, the tops had not been discovered yet. Okay? We only had the surprise that from meson mixing, D0, D0 bar mixing, the experiments found a much larger mixing than the expectation at the time. And the only way to explain that was assuming that the top was a heavy particle, and that's why we computed that. If it is a heavy particle, this correction is important. Okay. And now in this correction, motivated that the left detectors were upgraded, just to put silicon vertices and be able to measure precisely the BB bar. So having these self-energies and having that, this only depends on the top, does not depend on the Higgs. This depends on both of them. So you put the two things together, you can get information about the Higgs without discovering the Higgs. And of course, you get information about the top before discovering the top. So first, the top was discovered at Fermi-Lab in very nice agreement with the expectations for the standard model at the quantum level, okay, that the Higgs nobody found at the time. So here I'm showing the evidence of the electroweak correction. If you want the evidence for the Higgs boson at left. So what you have here is measurements of the Z coupling to leptons. So the vector and axial coupling of the Z to leptons. With that, you can cook something that is at lowest order equal to sin square of beta W. Okay. At higher order, it gets corrections, that's why it's called effective. And this is the decay width of the Z into two leptons, into an electron boson. And this is the same information, but this time plotted as vector coupling of the Z to the electron, or to any electron, an axial coupling of the Z to any electron. And here you have in different colors the coupling to electrons, muons, and taus, to see that they are consistent, so interactions are universal. all families have the same interaction with the W, and now you take the average of all the information, you get this black ellipse that gives you the 68% confidence level where this coupling should be here. Okay? Here is the equivalent thing. Here, electrons, muons, and taus are not separated in this. And now you need to compare that with your theoretical prediction. Well, the theoretical prediction in the standard model, just putting as the only quantum correction, the vacuum polarization of the photon, is here. So this I have shown before, that is an important quantum correction, but it's here and here. So it's outside the experimental measurement, which means that your precision is impressive, because you are sensitive to much smaller quantum corrections, which now depend on the Higgs and on the boson. Once you put the total electroweak corrections at one group level, next to the order perturbation theory, plus some next to the order corrections, the standard model prediction is this yellow one. And the yellow one depends on the top mass, and here the plot was done after the discovery of the top formula, which is 2005. So the top was already in a narrow, mass of the top was already known with some precision, and this direction is direction of growing the top mass. And this direction is the direction of growing values of the Higgs mass, varying the Higgs mass between 114 GeV, that was the lower bound put by that, and 1 TeV. And as you see, the agreement with the standard model is perfect, provided the Higgs has a low mass. Here, you see that even more clearly. It's the same yellow one, but only if you are in the really lowest range of the Higgs mass, you're okay with the standard. And that was one of the reasons why LHC was good. Because we were sure that we were very close. If that was not found at LHC should find something else. Because the relative corrections, the theory at the quantum level was successful and was showing indications for the Higgs. Okay, so how do you look for the Higgs? People have been looking for the Higgs since many years ago at different machines. Okay, from low energies to high energies. They always failed, obviously. There was no way to find the Higgs because the Higgs was not in the energy region that the existing machines were able to assume. What we know about the Higgs? We know that it couples to the W and to the Z, and the coupling is proportional to the mass squared of the tension. And it couples to the different fermions with a coupling proportional to the mass of the fermion, this time is linearly, and experimentalists like to put these kappas there, so that in the standard model, the kappas take the value 1. So this allows them to show results without units, which means that the units is the standard model 1. And how close the value is to 1 tells you how close you are to the standard model. Well, the first thing that you need is to produce the Higgs. Why is it so difficult to produce the Higgs? Because ordinary metal is done by upwards, downwards, and average. So if you take a 3 plus and minus machine, it's not easy to produce a Higgs because the Higgs coupling to the electrons is proportional to the electron mass, which is increasing. If you take a proton, antiproton machine, it's impossible to produce the Higgs with upwards and downwards. Because the values of those masses are so tiny that this coupling, again, is invisible. So the Higgs field should be everywhere, but we are not sensitive to it. That's why it's the first interaction that we know that it has been predicted mathematically, and we didn't have any experimental evidence of such a thing. Because the thing can be there, but it does not interact with us. So, what do you need in order to generate a Higgs? You need, for instance, to make W's or to make Z's. For that, you need a high energy machine. And then, once you have generated the W's and the Z's, they couple to the Higgs, so you can make a Higgs boson. And so you really need to go to high energies. But if you are at high energies, no LHC, LHC is a proton machine. Really is a proton machine. Because at high energies, the gluons, the valence quark content of the the proton is different. At high energy, the proton is a collection of many particles that share the proton mass or proton energy momentum, and is fully dominated by gluons. So when you are making proton-proton collisions at LHC, you are really making gluon-gluon collisions. That's the dominant thing. So the dominant production channel to make Higgs bosons is you collide gluons. The gluons generate top and bottom in this closed triangular loop. And now, since the top is very heavy, it comes to the Higgs and it generates. This is the next to dominant channel, and then as you go to the right, those are production channels that are there, but are less effective. So 90% of the Higgs events come from here. You need to use the Higgs as the first one, but then the Higgs decays. So you need to know the Higgs decay in order to identify it. It's an unstable. So again, the decays of the Higgs depend on these couplings. So what will be the dominant decay width of the Higgs? The heaviest final state that is accessible. If the Higgs was a very light particle, then it could only decay into electrons, maybe muons, and light quarks. So forget it. The probability of such a decay is very small. If you have a Higgs that weighs 20 GeV, it will decay to 1 okay. If you have a Higgs that weighs 500 GeV, it will decay into W sets and tons. So you can compute the probabilities, branching ratios of the Higgs decay to given final state as a function of the Higgs mass. This is the fourth standard model parameter that was not known. And depending on the value of this parameter, you see which is the dominant decay channels. For a very Higgs, this WW, then ZZ, and at a much lower rate, top and top. Of course, above the threshold for top production, it's 350 GeV. This is a logarithmic scale, so it makes a difference when you see the one line is below the other line. The Higgs has happened to be at 125 here. This has been a quite good thing. Okay, so the Higgs has made us the favor to have a mass such that we can analyze many final states. So we can fix many of the problems, otherwise it would not be impossible. So people were looking for the Higgs at lower energies. They didn't find that. Lead had some strange events that were never clarified. Fermilab had some strange events that were never clarified. And was only when LHC was put in operation that immediately in a very short period Higgs was found. Look into this other plot, because it's also very instructive. Here, what you have as a function of the Higgs mass is the total decay width of the Higgs. Again, in a logarithmic scale. And you can see that there is a tremendous jump here. And the jump is due to the opening of the gauge boson decay channel, WW, ZZ, and later dot. Okay, so the coupling becomes much larger, so you jump by 3 orders of magnitude in the size of the width of the Higgs boson. And it grows so much that, for instance, if the Higgs had a mass of 1 TeV, the width of the Higgs will also be 1 TeV. So if you think in terms of a right linear, it is crazy. Okay? You start with a narrow state. As the mass grows, the width of the right linear grows and grows and grows, and when you reach 1 TeV, it's flat. What this means? It means that a priori, 1 TeV was a possibility, but then physics will be non-recursive. You will have not seen just a peak. It will have been something much, much complicated, very similar to QCD, but at 1 TeV. Well, fortunately, it has been at 125, so it's here. And here means that the decay width of the Higgs is over MEV, not even TeV. It's an extremely narrow object. And it's an extremely narrow object because it cannot decay to W. Because twice the W mass is 160, and the Higgs mass is only 120. Okay. Nevertheless, you see that there is decay to WW here. What that means is that the Higgs decays into a real W and a virtual W, which means a W propagator that generates a Fermi pair. So it's a 3-body final state with 1 W and 2 factors, or 1 Z and 2 factors. But then it's not a real W production, you don't get the enhancement. Okay, whatever it is, the Higgs was discovered in 2012, and it was discovered in 2 channels. One is photon-photon, but the Higgs does not couple photons. How is it possible that the Higgs was discovered in a channel that it does not decay? Here is this. It's a very suppressed decay channel, but from the experimental point of view, it's a very clean channel where you can separate the 2 photons from the background. And what is the mechanism? Is you put this diagram in the opposite direction, the Higgs decay into 2 gluons. The Higgs does not couple to gluons, but it makes virtual top and p-top pairs, and then the tops decay into gluons. And in the same way, it can decay into 2 photons. That's the quantum loop correction. So the first discovery of the Higgs was through a channel, that the channel itself is a quantum correction. The other decay is a real Z and a virtual Z, and the 2 make a new plus and minus, and you can see the events. The events are very clear. So you have a proton that interacts with another proton, that is the huge Atlas detector. It's as large as the Sevilla Cathedral. And now you have a messy event with lots of things that you are not interested in, but you see clearly 4 lines that are 2 muons and 2 antimuons. And if you add the 4 invariant masses, the 4 energies momentum of the muons, you get the invariant mass of the Higgs, that is 125, so you get this signal. You see the picture. This is the Z. In the same way, this event, by CMES, you see 2 very energetic jets that go. Those are 2 photons. And you know that they are photons because your detector tells you that you have seen a photon with this energy. So it's a very spectacular event. Okay, so you see the Higgs. And of course, the signal is in the Higgs to 2 photon is just this small bump here. This bump has been growing as you have collected more and more statistics. So now we have very much precise measurements of these decay rates. So everything was very fast. We have been waiting 50 years asking the question whether the Higgs exists or not. I will say that many theories were convinced that the Higgs was not real. It was just in the same way as Gell-Mann thought that quarks were just a convenient mathematical language. The real dynamics could be something else. Many theories thought that the Higgs was not compelling. It was a nice mathematical development, but the real dynamics would be something else. But it happens that it was discovered, so it has been one of the fastest Nobel Prizes I am aware. In less than 1 year, they got the Nobel Prize, and even before the Nobel Prize, they got the Spanish prize. So the Fundación Príncipe de Asturias managed to be faster than the Nobel Prize. Let's look to the Higgs potential. Okay, remember, it only depends on the modulus of the scalar doublet, so only depends on the Higgs field itself. And there were two parameters. One was fixed by the vacuum expectation value of the Higgs. It was fixed already from muon decay. The second parameter, lambda, was unknown, but once we have measured the Higgs mass, everything is fixed in terms of the Higgs mass itself. So now we know the vacuum expectation value is around 250 GeV, while lambda is 0.13. So all parameters in the standard model have been fixed. So now you need to make predictions. Of course, this is fixed in the standard model, but we have never seen this coupling, we have never seen this coupling. So in order to be sure that we are testing the standard model, we should be able to experimentally test the cubic coupling and the quartic coupling of the Higgs field. That's difficult, but people will try. I have already shown before that just with the lab data, we knew that if the Higgs was true, it should be in a model. Okay. Now we can make this comparison quantitative. This is the W mass. This is the top mass. The green bands are the experimental values nowadays of the W and the top. This area here is what you get from electroweak corrections of the ZP. That means without information from the W, without information from the top, and without information from the Higgs. Okay, there is a nice agreement that uncertain these are not. Now you put the Higgs mass, that's additional information, and this narrows to this blue line. So the direct measurement of the top of the W and the indirect measurement of the top and W mass through quantum corrections agree. This is the same plot, but now it's the Higgs mass and the top mass. This is the measured value of the Higgs mass in red. This black band is the measured value of the top. And this is what you get from quantum corrections to electroweak observations. Therefore, everything looks up. We know very little about the Higgs still, but everything looks like the standard model seems to. Of course, the precision nowadays is still low. We need to make many other experiments in order to be sure, but it smells as a standard model. We have already strong evidence for the Higgs coupling to the top, because it is produced through tops, but also because very, very recently we have been able to generate tops through this subdominant mechanism. So it's the fourth mechanism in order of importance, but we already have events that correspond to this mechanism. So, and this gives a direct evidence of the Higgs coupling. In fact, it's better than that. With the data we have so far, we have been able to measure the coupling of the Higgs to the top, to the Z, to the W, to the bottom, to the tau, and very recently to the muon. This was supposed to be nearly impossible, but the LHC experiments have managed to do that. In this plot, what is plotted is the coupling of the Higgs to fermions and the square root of the coupling of the Higgs to bosons, so that all of them align in one line. So this line is the standard model prediction. And the plots are the experimental measurements. And you have two plots, because this is from Atlas, this is from CNS. And in the lower plots, what you are showing directly is the measurements in terms of these kappas. So the measured value of the coupling normalized to the standard model prediction of the coupling. And all of them, within uncertainties, are at the correct position of 1. Of course, uncertainties are large, as you can see here. Depending for the W and the Z, uncertainties are at the 5% level. For the other object, for the top is a little bit higher. For the muon, the uncertainty is at the 20% level. Because the coupling is smaller, it's more difficult. Okay? But so there is still room to play. We will likely have measurements at the 1% level in order to be sure. But for the moment, everything works very successfully. What else we have learned, and I am going to finish with that. Remember, I have shown before that the Z decay into nothing, into neutrinos, was telling us that there were only 3 families of line neutrinos. But that could be neutrinos to 45 G. Now this is excluded. And this is excluded because we are producing Higgs boson mainly through this mechanism. And this production is completely dominated by the top. It's completely dominated by the top because the coupling is proportional to the top mass. And then when you compute this loop, you get another factor of the heavy quark going through the loop times n Higgs squared over nq squared. So at the end, for an object which is heavy, so this is true in the limit where the mass of the object running along the loop is very, very heavy, what you see is the final result does not depend on the mass of the result. Only for heavy objects. For light objects, you have here a light mass that kills the process. That means that if there is a 4th generation, so there is a top prime and a bottom prime that are so heavy that we are unable to produce, they will be contributing to this loop. And they will give a contribution of the same order of magnitude as the top. So instead of the top, you will have top plus top prime plus B prime, a factor of 3 in amplitude, you square that, a factor of 9 in probability. So the probability to produce Higgs bosons at LHC will be a factor of 9 larger, and this is already excluded because the cross-section that is measured agrees with the standard model prediction within uncertainties, and uncertainties are at the 10-15% level, not the factor of 9. Therefore, the LHC data exclude completely a 4th standard model generation. It does not exclude our fields. Now you can start playing, you can invent a new physics model where you put something that looks like a 4th standard model generation, plus something else that cancels the effect here, but you really need to fine-tune many things. I would not call that standard model, it's real new physics. So that means that we don't understand why we have 3 families. That's the main thing I want to discuss tomorrow. But we know that there are only 3. It's not like in atomic and nuclear physics that you start having levels. Maybe if you look more, there is a more more and more excited levels that you can analyze. There are three and not one. Therefore, we can only get information from these three families, and those are the families that we need to explore. Okay, so let me conclude here. If there are questions or things which are not so clear, don't be afraid.
We can comment. Maybe can you put in the slide where you have the coupling of the Higgs to the different particles in this lining? Yeah, that's
This?
no, the other one. I'm saying that the first time that I saw this seminar, I was absolutely astonishing that the thing that means that you have a new particle, and it's also is something that appears unexpected, and then the point is that over a range scale, notice in the masses, in the case of all the known particles, notice on the other scale, that in this scale goes up by a factor of 3 orders of magnitude, so the number of events equals the square of that. So you have a new thing that you discovered that exactly indicates something that goes proportional to the square of the mass. Actually, it produces a tiny number for muons. With one, let's say the production of muons is something like 1 in a million when you compare to the production of probably 6. All the others fall in the line. And then if you, as not trivial, if you compare, for example, if you have a C particle, okay, that can behave, for example, in electrons, in muons, in taus, there in this factor will be proportional to the charge that is in the same plots. The decay of a C particle can be the same number in all, and then you have this decay that is forming over some many orders of magnitude. It was indeed very impressive. That this little bump that we discovered behaves so accurately over so many orders of magnitude, decaying all the new particles. For me, it was really impressive.
The bar that I have shown, okay, these are Z and photon means stop. So at this point, the only thing that we knew was top, Z, and W, but of course with much larger uncertainties. Now we know this because experimentalists have been able to measure the decay into bottom and bottom, the decay into tau and tau, and the decay into mu plus mu minus. They are trying to get channel to channel, but this is very, very, very difficult because the background is huge. So they have problems, but they keep that. What he was saying is that I didn't mention that this is a logarithmic scale. That's what makes the thing impressive. And that means that we don't know whether this Higgs boson is the standard model of Higgs. Okay? For that we need to, it smells that if it is not the standard model of Higgs, it looks like that. The uncertainties are what they are large. But there is no doubt whatsoever from this line that this is a Higgs particle. Because what this plot is showing is that the couplings of this particle to all other particles are proportional to mass in the case of fermions and are proportional to mass squared in the case of Lagrangians. So this comes from the Higgs couplings. What remains to be proved is that it comes from the particular scalar potential that I have had in my standard model. If you want in terms of this potential, and I will talk about that tomorrow if I can also, we know very well the value, the Goldstone bosons, because the Goldstone bosons are the longitudinal polarizations of the W and the Z. And we are making experiments with W and Z for the last 25 years. We know very, very little. In fact, I could say we know absolutely nothing about going up the field. Now we know in the standard model how the field looks like, because we have measured the mass, so we have measured lambda. So we know the potential is fixed, theoretically. But experimentally, we have never analyzed this. And we need to do that. If you want to think about that in a different way, that's the most important message we would like to give from these lectures, is that remember when the electromagnetic field was discovered. People discovered magnetic fields, electrostatic experiments. They didn't understand many things, they were just putting things. How many years it took between the discovery of the electromagnetic field and the real theoretical understanding of the electromagnetic field? It took a very, very long time. Now we have discovered that there is a fifth interaction. It's the Higgs field. What is important is not the Higgs boson, it's the Higgs field itself. It's a new interaction that was added by hand into the standard model of Lagrangian just to solve the problem of masses. And it works, which means that the Higgs mechanisms work, but now we need to understand this interaction. So we need to understand this work. And to check that really the interaction is what we were expecting. There are many other possibilities. And this we don't know. For the moment, the only thing that we know is that this fifth interaction is there. So everywhere in the universe, there is a field which fills everything, but we are not aware, or we have not been aware about this field until now, because this field couples proportional to mass. And unless you produce first very heavy objects, you can never excite the field. So it's the closest thing to a phantom you can imagine. It's everywhere, and you don't notice it. So tomorrow what I would like to talk is not about the things that we know, but more about the things that we don't know. Okay, so let's stop here.